Okay, so here we are back in part two of the central limit theorem. Just to recall from the previous video, we have an IID sequence of random variables, the xi's, expected value mu x, variance sigma squared. And what the theorem says is that the sum of these xi's, as the number of terms in the sum gets large, has a CDF that converges to the Gaussian CDF of the same mean and variance. And the way we formally sort of use the result and state it here is that we take the sum of the xi's, 1 to n, we subtract away the expected value of the sum, n times mu, and we divide by the standard deviation in order so that for each value of n, we have a random variable that's zero mean and unit variance. And then as n goes to infinity, this CDF converges to the standard normal Gaussian CDF, the phi function, although the font of this phi is a little bit funny looking. So then we did an example of how to use this, and in this video we'll do a few more examples. So this example is about digitizing an analog music waveform. It may seem vaguely anachronistic because it talks about compact discs and the data samples on the disk. Um, when this example was written, it was perhaps the mid 90s, and compact discs were everywhere. They had become a kind of a super modern high tech thing maybe 10 years earlier in the mid 80s. But here we are today, and I would bet money that most of you don't even own any compact discs. However, the digitizing music hasn't changed. The only thing that's changed is how that digitized music is stored. In the 80s and 90s, you stored it by stamping it into these compact discs. Nowadays, it's simply copied into some solid state flash memory in your phone or some other portable device. So even though you don't have a compact disc, the rest of this example is accurate in describing how the compact disc music standard digitizes music. Another thing that I remember about this example is that when we included it in the book in the early 90s, my co-author, Professor Goodman, explained to me that in fact, this way of sampling analog music waveforms was in fact his research at Bell Labs back in the 60s. And it took 20 years for that to be put into products, and now those products are gone, but the format and the mechanism still exists. So to get to the problem, it's a little bit complicated. There's an acoustic waveform, and that acoustic waveform is turned by a microphone and a transducer into some kind of an analog voltage and time V of t. And then at some particular time t, we have a sample of the voltage V, and it's analog. It has an infinite range of possible values. But we have to digitize that to store it in a computer. So in creating digitized music for the CD player, the voltage waveform V was sampled 8 times. There were 8 independent measurements corresponding to each sample. And so the way this works is that the true value of the sample would be V, right? And instead, you get each sample would be accurate um, within a half a millivolt of the true voltage. So these 8 sample measurements were x1, x2, up to x8, and each xi was a continuous uniform random variable with range from V minus 0.5 to V plus 0.5 millivolts. Then what the oversampling procedure does is it it combines these 8 samples. In particular, you form W8, the sum of the 8 samples, and then you form your best estimate of the voltage V, which is U, which is 1/8 of W8. To measure the quality of this average of 8 measurements, we calculate what's the probability that the average measurement U is different from V by more than 0.1 millivolts. If we show this is small, then we know that our averaging 8 measurements was good. Since W8 is the sum of 8 continuous uniform random variables, it's appropriate to approximate it by a Gaussian, use a central limit theorem approximation. And so both W and U are approximately Gaussian, and we can do this calculation of the probability that U differs from the true voltage V by more than 0.1 millivolts very accurately using the central limit theorem. So this equals the probability that U is greater than V plus 0.1 or U is less than V minus 0.1. And these two events are mutually exclusive, so it's equal to the probability of the sum of the two events. Because each xi is continuous uniform from v minus a half to v plus a half, the expected value of xi is indeed equal to mu. So e of v is equal to lowercase v. And so it's also true that e of w8 is equal to e of u is equal to v. Next, we observe that the variance of u is equal to 1 over 8 squared times the variance of w. And the variance of w, because it's a sum of 8 xi's, and they're all independent, this is equal to 1 over 8 squared times 8 times the variance of each xi. So it's equal to the variance of each x divided by 8. In fact, this is the key reason this procedure works. While the variance of this average of 8 measurements is 8 times less than the variance of any individual measurement. It looks like I'm writing smaller and smaller to finish on this slide, so maybe it's better if we just go to the next slide to finish these calculations. So we need the variance of x, and if you recall, x is uniform v minus 0.5 to v plus 0.5. So the uniform has parameters a and b, and this is a, and this is b. And so the variance of x, if you're planning on passing the final exam, you'll know this, right? It's b minus a squared over 12. And this is equal to 0.5 minus 0.5 squared over 12, which is just 1/12. So now we have to remember that the variance of u is equal to 1/8 the variance of x. And so this equals 1 over 96. The standard deviation of u is then sigma u, which is 1 over the square root of 96, which is about 1 over 9.8. And also remembering from the previous slide, the error event was the double-sided error, the probability that u is greater than v plus 0.1, plus the probability that u is less than v minus 0.1. And since e of u is equal to v, when we use the central limit theorem, we subtract away E of U, and we get probability U minus V is greater than 0.1, plus the probability U minus V is less than minus 0.1. And of course, we can also then normalize these quantities by the standard deviation of U. And, uh, and so now we have this is equal to the probability that the normalized quantity U minus V over sigma U is greater than or equal to 0.1 over 1 over 9.8, which is 0.98, plus the probability that C is less than minus 0.98. And of course, the Z is the normalized zero mean unit variance Gaussian. And so, in fact, these two quantities, these two probabilities are the same. And so the sum equals 2 times Q of 0.98. However, since our table for Q doesn't start until 3, maybe it's better to write this as 2 times 1 minus phi of 0.98. And you can look it up and you'll find out this is about 0.32. So the probability that the without the oversampling, this probability would have been 0.8. So this is a pretty good improvement. Because the binomial random variable is integer valued, the central limit theorem approximation isn't so good when you try to calculate probabilities where in small intervals where K2 is only a little bit bigger than K1. For this, there are better formulas. The best known result is the De Moivre-Laplace formula, which adds a kind of a zero point 0.5 correction factor to each term in order to get a better estimate. There are some examples showing that this is quite a good calculation when K1 and K2 are close to each other. These examples are in the book. I'm not going to test you on them in the final, so I'm going to leave them out of this slide deck just so as to not to distract you. At this point, you should be ready to take this quiz. It's another quiz where it employs a technology, computer disks with actual disks, that is perhaps outdated now. But the basic idea that, oh, the computer has to do 12 different things in order to finish the task is still something you need to be able to analyze. So the quiz is pretty straightforward and the steps are all detailed. So if you get stuck, you can always read the solution.